anyway, it's clear if you take any point in all possible translations, don't limit yourself to integers, you get all other points, right? So the equivalence class would be everything. So if you mod by everything, you just have one thing left. It reduces it to a point. That's probably why that's not interesting to look at. Okay, next result, corollary 5.19. Let G be a finite group of homeomorphisms of a Hausdorff space. Then I got distracted. Why do they have luggage? Very confusing. I need more posters for my door. All right, let's see here.
Put chalkboard paint on it.
The what?
Put chalkboard paint on it.
Don't tempt me. I do think the chalkboard paint on glass might be very nice.
It really would be a lot nicer for the chalk too.
Yeah. But you gotta have like a good way to spread it smoothly. That's the issue. Like a paintbrush leaves texture. You want like a foam brush, a nice like firm one. In some time, no children, dustless. Oh, I'm sorry. So if G is a finite group of homeomorphisms of a Hausdorff space, then X mod G is Hausdorff. It says just apply proposition 5.17, which was the one I've written there, to the case A equals X itself. Of course, X is open. Oh, of course, if G is a finite group, then 2 is trivially finite. But this is probably the most useful thing in this section, though. If you have any finite group of homeomorphisms of a Hausdorff space, then X mod G is Hausdorff. In particular, if you have a space, right, and a lot of times a reflection. If you take a reflection and it's usually its own inverse, right? Like reflect again, you back where you started. See, like the identity and the reflection forms a 2-element group. So this would say that that's Hausdorff if you mod by a group of reflections, which I think is probably important to know. All right, that brings us to the study of projective spaces. Yeah, I probably don't need this. I have a suspicion that these would work a lot better if I put a good coat of polyurethane on them before I started using it. I'm not sure though. But if you get enough polyurethane on something, it makes like a really like hard, almost plasticky surface, you know, like you get it in restaurants all the time, right? Imagine writing on like those restaurant tables that have like the thick surface over the wood. Seems like if you get enough of it, I mean, you have to like put about 3 coats on it and then like sand it with a really fine sandpaper, but eventually you get like really nice glossy. But it's the order, the fumes are bad though. I don't know. Sorry, I digress. Projective space. So, as he says, among the most important examples of quotient space by groups of homeomorphisms, we must include the real projective spaces, which he denotes P, N, R. Not to be confused with my stupid polynomials of order n over the reals. By the way, my definition for nth order polynomials over the reals is by no means a standard notation, it's just one I use in the course. So don't get too attached to it. This, on the other hand, I think is a little bit more standard. All right, but strangely enough, I don't have much use for projective spaces in linear algebra for some reason.
Should find one and give it to us.
Don't worry, we will talk about quotient spaces in due time, don't worry. There's that. By definition, PNR is the quotient of, what you do is Rn plus 1 with the origin removed, mod a particular equivalence. Which one is that? Well, let me say it's mod a group. All right, it's part of this larger story I've been telling you about homeomorphisms and a group of homeomorphisms. The group in particular, the group is the set of dilations. So G, basically what you're looking at is, let's say G from Rn. I need to give this to, well, fine, I won't. I'm about to call this X, but I'm stuck with it. Fine, I'll just write a little bit more. What's the formula? G of X is equal to lambda X for some lambda in the reals. And let's see here. For that to be true, what had I better say about lambda? I'm going to have trouble here if I let lambda equal to 0, right? So to be clear, it's the non-zero reals.
Oh, yeah, because the reals could have one.
The multiplicative group of the reals throughout the 0. And then in particular, what are the equivalence classes? So X, in other words, what are the group orbits by dilations? Well, X is equivalent to Y, right? If and only if what? Y is equal to lambda X for some lambda. Right, and here I'm assuming that X and Y are what? Not equal to 0. And of course lambda is also non-zero, but I suppose logically if I don't really need to put this here, strictly speaking, since it's forced on me by X and Y being non-zero, but I'll put it there for the sake of pedagogy. All right. All right. So he says, note that there's a one-to-one natural correspondence between projective n space and the set of one-dimensional vector spaces of Rn plus 1 through the origin. So let's picture it. P1R, for example, projective 1 space, what would that be? It's R2, right? Minus the origin removed, mod this, dilations, right? So if you want to picture that, you could picture it, right? Remove the origin. So the equivalence classes, the analog of my circles in the previous example, they're lines through the origin, right? So like this is an X, maybe this is a Y for lambda negative. So, and so forth. So this would be X. X2, et cetera, et cetera, et cetera. So P2, what would P2 look like?
Like a half circle.
So R3 without the origin, right? Dilations.
That'll be right.
Right. It's essentially the same picture. It's just 3D. So I get. you can't draw lines in 3D, as you may recall.
We know what you mean now.
Yeah. So for example, there's the one I can actually draw. Of course, y can be on the same side as well, but anyway, this whole line is, yeah. Okay. So, what's the topology we give to projective n space? Oh, this is wonderful. So, let Pn R have quotient topology. Induced by its construction, right? In other words, it's the topology which makes the canonical projection map onto the G orbits of the translations open. So what does an open set look like in projective one space, for example? What would it mean for a set to be open in P1R? Well, what he says here is he says the canonical map. All right, so the canonical map is this one, right? Pi is a mapping from Rn plus 1 with the origin removed to P. See, I can't tell my codes from my contras. It's very troubling. Kind of category would I have to be in? Is there some kind of category where contra and co is the same? Like a bi-category, perhaps?
I don't know.
Versus the contra equalizers.
The what?
Contra equalizers.
Contra equalizers.
I think that's sort of just a differential geometry thing.
There is actually some kind of deep significance to things where you can do both the co and the. Bill was telling me about this. There's
the self-dual category, maybe?
yeah. So I mean I can't remember what it was.
Like, that'd be where your category is equivalent to your opposite category, where the arrows are all flipped, I think.
Something like that. It is. I can't remember. It's fine. It's fine. Even if I could remember, I couldn't explain it. All right. So I guess again, can you tell me what a typical open set looks like? I mean, do we even have the right mental picture yet for projective space? I mean, you can try to understand it in terms of sets in the original space, but that might not be the right mental picture for the projective space, right? Points or lines in projective space. So if the inverse image of a set in PNR, right, is open over here, then that has to be an example of an open set, right? So open, let's say V subset of P and R means that pi inverse of V open in Rn plus 1. Now the reason you guys can't really answer that question is you don't even really have a concrete description of projective space yet. I've told you it's a set of equivalence classes, right? Is there some other like way we can kind of write it? Does that make sense at least though? Once we actually have a way to actually write a set in there. I guess I could just take, but I guess I can't, I mean, well, I think he says it's an open identification, doesn't he say? He says it's an open identification by proposition 5.515. So actually, that means I can look at an open set, right? If it's an open identification, that also means that if I take an open set here and project it, then that gives me an open set, right? So like, for example, if I took the, what's open in R2? Maybe this thing, right? Here's an open set. And then if I look at the projection of that into projective one space, it's like a whole fan.
Yeah, it's like all the lines that will pass through it.
Or yeah, it's like I think it's like you know what I mean. So all those, that collection of all those would then form an open set in P1R because it's the image of an open set in the plane. Okay. You're like, well, but I wanted to give the projective space. I don't like the topology you're giving on the projective space, right? You're like, I disagree with this topology. I would rather put the discrete topology on the projective space. If you were to say that to me, I would say, I'm sorry, but it's too late to topologize.
How long have we been waiting for that one?
That was. I definitely planned that, like at least a day.
No, I just thought of it now. But I've been talking about it with my brother for some time. It was his dream to work that into something. He had to find something that, I was like, you need to find something that's already got a topology, but... And this is a good example to do that joke on, right? Because once you construct something by the quotient topology, you're stuck with the topology. You can't unquotient it. I mean, the topology is built into the stupid construction of projective space, right? You don't... It comes built with topology built in. So it is too late to apologize. See, that joke has that joke is not going to work very soon. Like, you guys know what I'm talking about, but it won't be long before that song is long forgotten. Sure. As it ought to be.
I don't think it was that bad.
No, it was a good song. But they played, you understand, they played it to death, though. I mean,
Well, that's all radio songs. That's why I don't listen to radio
Yeah.
anymore.
Oh, yeah, fair enough.
I could see that being a parody video.
A really, really nerdy low view nerdy video on YouTube.
I remember. Did I show you guys? I don't think I've shown you guys the Perlman rap, have I?
The what?
There's a I showed it to elementary differential geometry, that very rare course that we somehow got to run. And one of the students, after seeing said video, said, "I can't unsee that. I can't unsee that." He was disturbed by it. It's.
That's why I'm showing it to you.
Is it called the Perlman rap?
I'll have to find it. I'll show it to you guys. But our precious time is dwindling. And there is something I want to get to here while we're at this, because there's something nice to add to these pictures. So you can look at the inclusion, all right? The inclusion. Oh man. Excuse me. What else lives in Rn plus 1? How about this? The n sphere is naturally included in Rn plus 1 without its origin, right? Right? And then if you go from there, so let me draw a picture, say that this is I, right? So you start with here, I, then pi, right? Then we're over here to p, pnr, right? So in fact, he says this composition, right? Let me see what's the composition. You can, right? Pi composed with the identity, right? This is a mapping from what? From n sphere.
It's 5 o'clock
It'll be
p.m.
on 2, right?
Right. This is onto. Right. And
2 to 1.
Hmm?
2 to 1.
I think that's right. He's like, if you look at, he says I'm not sure what he means here. He says it factorizes through a continuous bijection f. Wait, what is f? He starts talking about an f, but he hasn't said what f is. I'm missing it here.
I think that would mean, wouldn't f be from Sn to PNR? And he's saying the composition pi of I would be equal to f.
I'm tempted, I want to say that f is equal to pi composed with I. Well, but no, that's not quite right. Because
Because
he's,
here makes f go from.
f goes from the quotient, all right? So he's like Sn quotient tilde. And he's about to tell us what this equivalence is. That's the antipodal equivalence. Okay, you know what he's saying? He's saying, suppose. No. Now this one right here is x is equivalent to y if and only if x is equal to minus y, or x is plus or minus y. We claim that f is a homeomorphism. Let me draw that. I think you guys are right. I just think something's lost in translation here, maybe. So you look at this diagram. We have Sn includes into Rn plus 1 minus the origin, right? And then that he's got a mapping R. What's R? He tells me that. What is R?
Just gives the unit vector.
Oh, it's the unit vector. It's the hat map. Put a hat on it. And then he's got the pi. He calls it pi prime, pi, and is a pi prime again. Pi prime, I assume, is the canonical projection map with respect to the antipodal equivalence on the n sphere. So this maps points in Sn to pairs of points. Yeah. So this would be Sn mod that equivalence. This is P n R. This, of course, is again S and mod the antipodal equivalence. x is r of x, just to be clear, r of x is equal to x over the norm of x, which makes sense because we're in the non-zero space, so we can take a unit vector of any non-zero vector, as you remember from physics, or Calc 3, perhaps. He says this is F inverse.
It's a nice looking picture.
The thing driving me nuts is he just never defined what F was. I think he's like just missing like a little half sentence, let F equal block. And then everything else would be clear. I don't see where he said that.
Can it just be defined as like the composition?
See, I think so.
I compose with pi prime inverse.
Let's see, he wants F to be a mapping from the antipodal equivalence space to projective space, so it would be
So it would be pi compose with pi prime inverse.
but that's not the inverse map doesn't exist, right? Maybe that's the issue. That's he can't write a formula for it, but he can define it in terms of these diagrams and some sort of universal principle, right?
And I think we probably could write the formula for it.
What is it?
Because you could define, like take the point and send that to the line that point goes through. And then you just have to show that that's well defined under the equivalence relation.
Yeah, right. I mean, I think I can draw a picture of the map, right? The mapping is this. It's unfortunately the fan. Oh well. So here's S1, right? S1, but we're looking at S1 mod the equivalence, right? So that's actually like
Set of two antipodal points.
like these are identified, however you want to illustrate that. And so you're mapping these pairs to corresponding what? Corresponding lines. So what you do is you just take the diameter through the points and extend it. I mean, that's the map. It's a natural map. On the flip side, you see that the points, well, pairs of points on the n-sphere give you natural representatives for the projective lines. Right? So like any line here, I mean, you can envision the 3-sphere here, right? 2-sphere, rather. And so like this line cuts through this pair of antipodal points. So that pair of points is identified with that equivalence class. And so we can trade projective n space for the n-sphere mod antipodal points. What he says here, he says both the inclusion and the map R are continuous, and likewise pi composed with I and pi prime composed with R is continuous. By proposition 5.8, F and F inverse are continuous. Well, what's proposition 5.8? Proposition 5.8 goes back to if you have a continuous map F, and I mean 5.8 is basically the thing that was built over the universal property of identifications. But 5.8 in particular said if you have a mapping. Oh man, I just lost it again. There we go. If you have F from X to Y continuous, right? And there's a projection right onto this, then what happens?
There exists a continuous
G.
G.
And what do we have? We have
G composed with pi is equal to F.
yes.
G is constant on
Right, yeah,
the
exactly.
classes.
Yeah, if and only if, in this case, if only if f is constant on the equivalence classes. G is a mapping of equivalence classes, so it can't help but be continuous by single valuedness. Sorry.
So the lemma you're using here, this was the universal property for identifications.
It is. It's proposition 5.8, which is essentially a corollary to the universal
Okay, yeah.
property for identifications in the section 5.1. So he's saying, oh sorry, getting back to it. So what is it saying here? Where were we? I'm trying to see. So he says pi composed with I and pi prime composed with, so pi composed with I is what? In this picture, pi.
So it goes from Sn to Pn.
It goes from Sn to this, like this. So that's continuous. So you can look at like Sn to Pnr, this map, right? Then you got the projection pi prime down to Sn mod tilde, right? So then basically by that universal property we get this mapping here, which is called F. Does that make sense? And likewise over here, pi prime composed with R.
Composed with that, right? No.
Yeah, pi prime
Yeah.
composed with R. R goes first. I know it's just this always this fight we have with the order of composition, you know? Get over it eventually. So again, you can basically get, this is the, these are the by universal principles of identifications, those exist. The F and the F inverse. Okay, so more to the point then, what was, let's get past this initial stuff. Because Sn mod the antipodal equivalence is what? Here's what I was mentioning to you guys earlier. What is that? What is the antipodal equivalence though? Think about the homeomorphisms on the n-sphere. Right? You have inversion. X goes to minus x. That's, if you invert again, you get back where you started, that's a 2-point group. Right? So this is, in fact, equal to Sn mod the group G, where G is just equal to plus or minus the identity map. By the way, inversion is minus the identity map, right? So that's pretty cool. And then, but and as he points, this is a subgroup of the homeomorphisms on Sn. So as you say, what's the takeaway from this? Corollary 5.9 then, 5.19, implies that real projective spaces are Hausdorff, because they're formed by taking this topological space and quotienting by the finite subgroup of the homeomorphisms of the space. I'm happy about that, because the thought of checking Hausdorff directly on the projective space does not excite me. You see the frustration of these spaces, like the way we describe them is so hands-off, right? So the rest of this section is a little bit more hands-on. He actually starts to give us some formulas for coordinate charts on projective space. Projective spaces are actually important examples of real manifolds that I would say they're not directly, to me they're not directly embedded. I don't know if you can really say they're in Rn per se. There's, like, okay, fine, there's the Whitney embedding theorem says that like any finite dimensional manifold can be viewed, you can immerse it, you can look at a diffeomorphic copy of it inside Rn, such that you can look at the manifold as just a subset of n vectors for sufficiently In. This is Whitney's embedding theorem. Nash proved something similar and even deeper. If you have a manifold which also has a metric, which is the notion of distance, you can even isometrically embed a manifold, such that its intrinsic geometry then appears as the extrinsic inherited Euclidean geometry induced from the metric on Rn for sufficiently high. Like those theorems, those embedding theorems by Nash are like, well, that's why Nash is famous, I think, in part. And there's like game theory stuff, who cares? But sorry. And he had friends. Let's see here. I think I'm going to leave these formulas for next time because they look super fun. So next time we'll do the formulas for projective space and try to wrap up this chapter, hopefully. Maybe we'll get started on I hope we get started on sequences next time. So I think that's a pretty good point to stop. Unless you guys want me to go through the formulas, in which case I will eat some candy, rally, and start again. No? Okay, I think
Oh. I usually wait, like, hear your clock, say like 5 o'clock. And I'm like, man,